Cool. I will start with this quote because I think it's an important one. I laughed when I heard it this morning. If you don't take anything that I'm going to say this morning, just take it. It's not easy. It's a form of art to be capable to produce microcapsules. Dave this morning was talking about the process for forming emulsions, which is a form of art by itself, which is the membrane emulsification, the CXF, microfluidics, etc. And on top of that, a different art, it's the art of kind of producing the shell. Swelling, would you like to share some experiences?
I didn't. Actually, I'm just like with you because I didn't have a good experience working with this.
Yeah, I think sometimes it can be a bit easy for people to think that it's only about mixing things and the capsules will assemble itself. It's not. There's a lot of dedication and a lot of hard work on that as well. So if you don't take anything from this talk, just take that it doesn't sound very easy and it's not easy to produce all these capsules most of the time. But why do we do it? I made the, I'm curious about trying to make this video work. So why do we do it? Because when we are talking about microcapsules for self-healing, they can be easily added. So those are lump sum are some of the microcapsules that Dave was describing this morning. And they can be easily mixed when we are producing concrete. And they can protect the healing agent that it's then going to be released later on when there is a crack. It's very, what's the word, enticing for kind of self-healing technology to be capable of using microcapsules because of those reasons as well. And when we think about the history of people investigating microcapsules for self-healing, I think the first paper that I remember seeing was some papers with monofluorophosphate back in 2011. And I think the Pelletier paper with sodium silicate in polyurethane shells it's also from 2011. Some earlier documents, when you think about the history, today it's a history class. When you think about the history of self-healing, there are some early documents of kind of vascular systems with dry in the early 90s. But when we are talking about capsules, they start in 2011. And it has been a lot of progress since then from all the materials that, all kind of materials, from minerals, for epoxies, from spores, MgO, and all the way to, I need to update this graph, but all the way to 2020. And I think one thing that I want to highlight here, or two things that I would like to highlight from this kind of process of producing microcapsules, like now it's been 10 years that people have been investigating microcapsules for self-healing, is that first, there are traditionally kind of two methodologies to produce these microcapsules, broadly speaking. Either we are talking about having a liquid core for these microcapsules, and then those are all the processes that Dave was mentioning this morning, because then what you have to do is to produce an emulsion of this healing agent that is going to be your liquid core, and then deposit a shell on the interface of that emulsion, and then you have that core shell structure of the microcapsules that you want. It's either that way, or the other way, if you're encapsulating a core that it's a powder or a solid core. This is typically going to be in a pellet format, and that pellet is going to be covered with something. And Shipriya is going to talk a little bit about that as well, to kind of protect the core. Under that umbrella of pen coating, it's also when we are talking about impregnation. So if you have a material that is then impregnated with spores, for instance, is a classic example, then that material can be coated as well. And another thing that I think that it's very important to mention at this stage and for you to bear in mind when you're reading papers that are using capsule-based self-healing as well, is that the characterization step, it's very important for these produced microcapsules, because it's very easy when you hear Dave saying that you pour this phase in that other phase, and then you change the pH, and then the shell, the swelling is laughing. It's very, it sounds like making a cake, isn't it? You just pour in one thing and the other, and you change the pH, and then you form the shell. It's not that straightforward, and not necessarily because you mixed everything together, the capsule was formed. So there is the need for characterizing these capsules using optical microscopy, scanning electron microscopy, that then is going to provide that core shell structure to see the details of the core shell structure and the morphology of these capsules. Doing thermogravimetric analysis to know more about the stability of these capsules, and also the content of shell and core material when these capsules are produced. Using infrared to characterize the moieties in the capsules, the chemistry in the shell of these microcapsules. And encapsulation efficiency, that we are lucky enough to have an expert on microcapsules just discussing that this morning here, but not necessarily everyone that is producing capsules in the literature are discussing kind of what encapsulation efficiency they are producing as well. And it's quite a valuable information. And on top of that, after we characterize, kind of investigate the methodologies for producing the capsules, characterize the microcapsules, it's also necessary to investigate the properties of these microcapsules for self-healing. So we are talking about, amongst other things, the effect of these microcapsules on the strength of the mortar, the concrete, the cement paste, or whatever you're investigating with. Typically optical microscope image to see the crack healing. So I don't think I need to explain that at this point, but yes, so there is a crack. The crack will open the capsule, release the healing agent that it's going to kind of deposit in that crack. So one way of observing that is observing the healing of the crack, kind of the crack mouth open. Permeability tests are very valuable here as well, because then we are going to be talking about the recovery on the transport properties. Doing SEM and NDX to identify what kind of products are being formed when we are talking about the healing products in that crack. And also CT scan could be a very, very valuable technique for identifying the position of the products in the healing of the crack as well. And in a way, I'm bridging with the work that Gabriel is doing, because he seems very isolated there. But when we're thinking about self-sensing as well, there is one paper that is quite interesting that is talking about you have a crack, and the conductivity or the sensing properties of that material is halted because there is no transmission from one side to the other. But then when we have the position of the healing products in that kind of interface, then we have a restart of the conductivity properties, and then we can have a sense of healing by using self-sensing. So that could be a valuable technique for kind of investigation of self-healing through self-sensing as well. I'm going to give 2 case studies today, and I hope that I don't talk too much. But I also think they are interesting from a point of view of kind of progress of how this group has been investigating microcapsules for self-healing. And the first one, which is makes sense, is the continuation of the work that Dave was presenting this morning, which was back in 2013, I guess. There was this question of, would it be possible to encapsulate a mineral healing agent in those kind of capsules and then investigate the healing properties of these mineral healing agents? Because if you think about it in terms of kind of history as well, when we think about self-healing, one of the first papers that come across is that 2003 paper from Souza's group in the US, that they were investigating capsules for self-healing. And if I'm not wrong, it was with DCPD. So translating that technology for a kind of cementitious matrix, would it be a sensible idea to think about sodium silicate as a core, as a healing agent that would be encapsulated? So I think that was the question that we started with. So the first step, of course, was the encapsulation of sodium silicate, and that's what Dave was covering this morning. So they decided to use complex conservation to form this shell. There were several investigations, so kind of that's a batch system. There were several parameters being investigated, such as the agitation speed that it's used, repeatability and agitation time for producing these capsules. And one important thing to mention here, that it was another parameter that it was investigated. It's a little bit of what Dave was talking this morning. That is, right, hydrophobic and hydrophilic compounds. So when we're talking about using emulsification polymerization, the principle of it is that you have a droplet of something and the shell is going to deposit on that. And to form that droplet, you need a hydrophobic compound, just kind of in a hydrophilic. And hydrophobic mainly means that that thing doesn't like water. That's what's called hydrophobic. And the hydrophilic part likes water, right? So you have that droplet of oil dispersed in the water. So when we are using complex conservation, having this oil-water system, it's very precious. That's what we want. But sodium silicate, as you all know, it's a hydrophilic compound. Sodium silicate, it's diluted in water. So clever people, how was it made possible for the sodium silicate to be encapsulated using complex conservation? Have I lost you already? Are you still with me? A way of doing that was to creating an emulsion with sodium silicate in oil, and then the position of the shell was in that interface of the oil. So we are not talking about a capsule that is kind of purely sodium silicate inside. We are talking about around 40% of sodium silicate dispersed in an oil phase, and then encapsulated with a gelatin gunarabic shell. And when we are talking about this production, the size was an average size of 200 to 290 microns, and the shell thickness of this gelatin gunarabic system, it's around 5 to 20 microns. But well, yeah. But I think when we are talking about, when I was talking before about the importance of fully characterizing the system as well, I included the thermogravimetric analysis to investigate the thermal stability of the shell, because you want it to be, well, to prove that it's stable. Some DMA analysis to investigate the mechanical properties of these shells. I don't think that's the best SEM that I've ever seen in my life, but what is basically showing here is the shell of that capsule after it was dried. And one important property that it was noticed of these capsules after they were, or one important property of these capsules is that when they are wet, they are very rubbery as gelatin when we're playing with gelatin. But then when they are dry, they're very, very brittle, like those gelatin sheets when you buy it in the supermarket. And that's very, well, it's very precious when we're talking about self-healing, because then what you want is that the capsules are going to survive the mixing because they are rubbery. It will help with surviving the mixing. But then when they dry out, they are very brittle, and the crack is going to easily trigger the microcapsules as well. and FTIR for characterization of these capsules as well. And another thing that I didn't mention, but I'm mentioning now, it's that stability of these microcapsules on pH, because you will, of course, want this capsule to be stable at high pH because it's the pH of the matrix. When these capsules were embedded in cement paste, it's quite interesting because then you can see the release of the core immediately. I don't think that's the best image, but as soon as you break that capsule, you can see the release of the oil coming out of the capsules. They have a very good bond with the matrix, which is quite valuable for the capsules as well. And it's interesting that they are fluorescent under the UV exposure as well. So you can clearly see those capsules using optical microscopy as well to investigate kind of the homogeneous dispersion of these capsules in the cementitious matrix. When we were assessing the self-healing of this microcapsule, the self-healing capacity of these microcapsules, so those are the concentrations that were investigated for these microcapsules. And what we see is that, yes, there is an increase of viscosity and a decrease in compressive strength by adding these microcapsules. It could, and that's an interesting point. So when we were talking about the crack mouth healing, it was around 0.2 microns. But also it was noticed a decrease in the crack depth by adding these capsules for self-healing. And another interesting detail to discuss here is that even though, so when we are talking about the sodium silicate for promoting self-healing, we are expecting that the CSH would be produced in the matrix. That's kind of the reaction that we were relying on. And even though the crack mouth healing wasn't the best one compared with the literature, we have papers of capsules being capable of healing up to 1 millimeter of kind of crack mouth healing. We observe a very good recovery in the transport properties after adding these capsules. That means that even though all the healing products were not necessarily deposited in the crack mouth, when we are thinking about the crack being like a tip, some of the healing products would be deposited in the kind of the end of that tip, isn't it? So then we are going to have the recovery in the transport properties, even though the crack mouth healing wasn't 100%. And that's where, when we look at the Giannaro's paper, if you haven't come across 2016, Petrus was talking much more about the crack sealing properties rather than healing itself. Of course, there is to do with mechanical properties as well, but yeah, we're talking about the recovery and transport properties. So after this capsules were tested in the laboratory, we thought about kind of testing that in a large scale field trials, and that happened with encapsulating 8% microcapsules by volume of cement, and producing kind of those slabs with microcapsules being casted. And I think one thing that it's interesting to point out here, well, there are several interesting things, but one, it's the sheer volume for producing that, which is quite larger compared with the lab test that we are producing before. And what we see are results that are similar-ish to the results that we observed in the lab. So a slightly reduction in compressive strength, 63% of crack healing after 28 days, the reduction in crack depth, permeability recovered by the same mechanism that I was discussing before, some strength recovery with the microcapsules, and it was observed CSH and carbonation products being formed in the crack kind of healing. Oh, this is the mechanism of healing that I was talking before, but in addition to that, this was in Wales. And what is Wales famous for? Yes, it was raining quite a lot. So that's what the schematics was here as well, showing that even though the healing products were deposited here, some of the healing products may have been washed away by the rain as well, which is why when we are discussing the results, the daily rainfall total was included in the results as well. After that, we had 2 commercial applications. So the first one, hopefully Abir is going to be showing those, no? Shipriya. So hopefully Shipriya is going to be showing that. We produced some blocks that are here in the same building on the top of the building. And these blocks were casted in the wall containing microcapsules, and also some outdoor reinforced concrete slabs in the Dyson building that you guys were yesterday. So that's the video that I was showing in the beginning. And these labs are outside. The properties of the inclusion of these microcapsules in the systems, they're being characterized for this system. So there is characterization going on. Acrylic published a paper with the results of these labs as well quite recently. However, which is a comment that we see quite often when we're talking about large-scale implementations of self-healing technologies, there is no crack quite yet. So we are not quantifying healing happening on these capsules or on these systems containing the microcapsules. Another thing that I would like to cover when we are talking about the microcapsules containing, the gelatin Arabic microcapsules was a work developed by Beni. Beni is going to present some of his work on the talk with Shipriya in a bit. But he also investigated the use of the same microcapsules for self-healing of cement bentonite cut-off wall materials. And what he noticed was an increase in the compressive strength of the cement bentonite systems and an autogenous healing of these cracks. 75% of the cracks, when we are talking about a crack that it's larger than 0.15 millimeters, sorry for that, yeah, and a recovery in permeability as well. So here we can see some of these capsules in the cement bentonite system. So the idea is the application of this kind of self-healing systems for geotechnical applications, and the healing products around the microcapsules. You can see here, it was characterized with EDX. Beni also did a fantastic work when we were talking about kind of trying to investigate the healing products on the cracks. And he did that through CT scan. And what he did was to have a very kind of, any one of you have tried to work with CT scan here? The key point about the CT scan is that the sample needs to be really small when we are thinking about characterizing any products, because the size of the sample is going to be relative with the definition of what you're saying as well. So if you want to see small cracks, you need a small sample. So Beni had some small samples of cement bentonite that he cracked and incubated for 28 days in a high humidity environment. And then he observed that same sample again under the CT scan. And what he observed was some rupture microcapsules that he observed using the CT scan, but also the crack filling of some of these capsules with the healing products associated with sodium silicate. Yeah. So we're going to move to the acrylic microcapsules or acrylic shell microcapsules. Sorry, when am I supposed to finish this? Now? Okay.
Absolutely.
Okay. This project is very close to my heart because it's something that I've been working with it for quite some time now. So if I get emotional, bear with me. I'm just kidding. Yeah, so changing from that capsule that we were talking before, it was a gelatin gonarabic shell. Now it's changing to acrylate shelled capsules. Right, microfluidics for the production of microcapsules. Here, what we are talking about is a methodology for producing emotions. First, let's start with that. And we're going to use, I was using microfluidics for producing emotions that would be then capsules. And you're going to see that in the lab today. The main thing about microfluidics is that the channels of a microfluidic ship are very small. So with that, what you have, it's a laminar flow. So you don't have the turbulence that you would observe in a kind of traditional mixing system. And because of these channels being very small, what you can do, so this is a traditional microfluidic ship, and that's the inside of the ship. So what you can see is that you have one channel pumping liquids and coming across another channel. And here you can produce what we call a single emotion. So that's what Dave was describing this morning so well, which is just like a droplet of oil in water or water in oil. But using microfluidics, you can use a second channel here that then you can produce a double emotion. So a droplet of water surrounded by a droplet of oil, surrounded by water as a kind of continuous phase. And why this is important? Because then you can use that double emotion as a template for producing microcapsules. And you do that by exposing these double emotions under the UV light. What happens is that that middle layer polymerizes and you have a solid shell and a liquid core. Very often people ask me why I decided to work with microfluidics. And the main point against that is, of course, the amounts of the quantities of material produced. But I think when I started reading about capsules for self-healing in general, I could see a lot of results that I wish there were more kind of detailed discussion on how this material was produced and the characterization of this material as well. But on top of that, I think one big question that I had back then was around if water is so valuable for producing some of the self-healing products that we are talking about, why we cannot just encapsulate water and disperse these healing agents in just a water phase? Hopefully it's a question that you may be asking, but hopefully not, because you've read my paper and you know that it's very tricky to do that. Water is a very small molecule and it's very hard to be retained inside of kind of thin shells that we are talking with capsules. And what happens is, even if you produce a capsule, so this is a double emulsion containing colloidal silica inside. This is a capsule containing colloidal silica. When you dry that material, you just have the colloidal silica being retained inside of the shell and all the water kind of leaks out of the shell. But that per se, it's not the biggest problem. The problem is that sometimes when that water is coming out of the shell, what happens is that that capsule may buckle as well. And it's a much bigger problem when we are talking about the loss of that aqueous core. Interesting, one of the things that I did during my PhD as well was to encapsulate sodium silicate. And in this case, what I did on a Wednesday afternoon was to just try to encapsulate the pure sodium silicate with the acrylate shell, using that laminar property of microfluidics that I was talking about, that the two chemicals are not going to mix directly. And this is important because sodium silicate, it's very alkaline, it's very reactive. So you want a system that is stable enough for encapsulating the sodium silicate. So these are the double emulsions, and those are the capsules observed under SEM. And what you can see is that the sodium silicate is so dense, the density of sodium silicate is 1.5 grams per liter, grams per ml, grams per ml. Stick with grams per ml. It's a lot denser than the droplets of the oil. So what happens is that the sodium silicate escaped from the droplets of the oil during the polymerization. So that's what you have, that kind of, it looks like a mouth opening. It's just that during the polymerization, the sodium silicate was leaking. To cope with that, there are some alternatives, but basically we need to play with density. One alternative is, again, to kind of dissolve that sodium silicate on an organic phase, because then you adjust the density of the system, and then you can produce the capsules. But again, they are emulsion kind of shape. Organic cores are a lot easier to encapsulate when we are thinking about using techniques in general for producing microcapsules. And on top of that, because the molecules are a lot bigger, they are retained inside of the shell a lot easier as well. So those are kind of classic examples of double emulsions and microcapsules produced with an organic core. And on top of that, because of things that I don't have time to explain, the shell, it's a lot thinner when we are working with an organic core. And of course, they are a lot easier to trigger as well. So here we are talking about a shell thickness that it's around 1 to 2 microns. Using microfluidics, there is also the chance of functionalizing the shell. It's not only to microfluidics, but it's a process that very often you have to do when we're talking about microcapsules. Because not necessarily there will be a good interfacial bond between the capsule and the cementitious matrix, or you want to increase that stability of the microcapsules. And one way of doing this is by investigating the the functionalization of the shell with hydrophilic groups. So there are groups that are going to bond better with the cementitious matrix. Yeah, so when we're talking about physical triggering, those are the parameters that we want. A capsule that has non-aqueous core, some hydrophilic shell, and some thin shell to be physically triggered as well. I also investigated microfluidics to produce capsules that are pH triggered by putting a pH sensitive chemical inside of that acrylic shell that will be then triggered by a change in the pH. So that's the idea, that when we have an alkaline pH, we have the retention of the core, and then the core would release when the pH is decreasing. That's very challenging. Any of you know why? Or did I lose you already? 7 slides ago. Any idea of why that could be challenging? No? Okay, that's a homework for you guys. You can only do punting on Saturday if you know the answer to this problem. Otherwise, no punting for you, no pins for you, and no tour for you. Moving along, and that's coming close to the end of my presentation. Of course, the problem with using microfluidic is that the quantities are really small. We are talking about 1 gram per hour of material being produced. So one way to deal with it, it's quite similar to what Dave was proposing, which is the parallelizing, putting several of these microfluidic ships in parallel. And then what you do have, it's a higher production rate of these systems. So so this is kind of the face of the microfluidic ship. You're going to see one in the lab in this afternoon. This is the type of capsules that are being produced. It's quite similar to the results that I was showing before. But here, what I'm showing is an aqueous core with amine being encapsulated, so it's a kind of different liquid phase, and a larger capsule as well. We're talking about 500 microns. We can control the shell thickness of these microcapsules when we are produced by this equation. So when you increase the inner flow rate, you decrease the shell thickness of these capsules. So you can work from thick, which is not interesting for us, all the way to thinner shells. Playing with different acrylates that are going to offer a better bond with the cementitious matrix as well. So this is an SEM of these capsules in cement paste. And here is the beloved CV that Dave was talking about. So now here, when we're talking about the production of these microcapsules, we're talking about, for the double emulsion, we can have a CV around 2%. And for the microcapsules producing over 7 hours continuously, we had a CV of 5% for the production of these microcapsules. An important thing to notice here are those values. So we're talking about around 13 grams an hour for a single ship, but then you can put up to 6 of these ships in parallel for producing those double emulsions, and up to 1.5 kilos of these capsules per day. This is a slide that I was talking about, kind of the cost of the introduction of these microcapsules. And it's very interesting to see this Leachgate market research showing that people would be interested in buying the technology or using the technology if it would mean just an increase in 20% of the price. And this would be something that I would be talking about technical readiness level, but it's a little bit short of time. But I think I want to invite you guys to think about, when we're talking about technical readiness levels of all these technologies, where do you think, and that's homework too before punting, otherwise no punting for you, where do you think those technologies would be? And that can be a very valuable exercise when you're thinking about your PhD in general as well. Yeah, that's it. So in conclusion, I was discussing the potential of these microcapsules for cementitious systems, this range of laboratory tests, challenges for encapsulation. And if you don't take anything from this talk, just remember it is challenging to produce microcapsules, and field trial and commercial application of these microcapsules. I'm really sorry I'm over time, but thank you very much. Any burning question for you?
So what is the smallest capsule that we can see in a CT scan?
Ooh, that's a very good question. You can see capsules around 80 microns. You can't see the shell of these capsules. And also they are very similar to the pores of the cement paste. So you need to, it's very tricky to differentiate what is a capsule and what is a pore. But you can see that they are there. And I know that because I was producing very monodispersed capsules. So they are all the same. So you see over capsules that are pores or capsules that are all the same size. And then you can see that there are capsules. Yeah. Yeah.
In my case, I use concrete with fibers. I use concrete with fibers.
Yeah.
Do you have any recommendations for using capsules in green light? Also, because as far as I understand,
Yeah, it's tricky, isn't it? Because we're talking about the expression of the fibers and the capsules around it.
Should I use the fibers, steel fibers, for the very to control the practice?
Yeah.
For my samples. But if I went to use this
I think maybe well, let's think about that together. I think one way of thinking about that, potentially, you should think about the size of these capsules as well. Because then when you're working with fibers, the size of the capsule is going to be fundamental, isn't it? So if you're talking about massive macrocapsules, we deal with a problem. But maybe playing with smaller sizes could be a solution for using fibers to disturb the capsules. I think there would be some interaction that needs to be investigated for sure. Yeah.
I have a question. We were talking about the bond.
Can you speak up, please? Can you speak up?
Oh, yeah. Okay. You were talking about the bond between the concrete matrix and the microcapsules, which is very good. My question is, how is the bond between the rebar and the microcapsules if they get in contact? Because, you know, when we are loading, we rely on the bond between the fibers, the rebar and the concrete matrix, and we use the analysis and see how it works. So, does it impact the results that we are going to get when we are, for example, testing it for textual?
Yeah, because the mechanism is that that capsule is going to be dispersed in the cement phase. And the importance of the bond of the capsules and the cement phase is going to be, the honest answer is I don't think that the bond of the capsule with the rebar is going to be very good. But at the same time, if you think about the surface area of the cement that it's in contact with the rebar, it's not that, particularly when you're testing in the lab, I don't think it's that large, isn't it? So, yes, the bond with the rebar will be really good. Yeah.
If we can add to that, it will be like small voids. So in the interface, you might have voids in normal concrete, right? So when there is a micro capsule interaction with some steel bar, that will be like a void. It will be at some specific places. So you are talking about a big beam, and so the interaction of the micro capsule at some specific points will not disrupt the bond mechanism as a whole.
Well, I think that also depends on what proportion of microcapsules we are using.
Yeah.
Because if we are using a lot, then
Yeah, for sure.
well, that was my another question. What percentage of microcapsules I should use in my large scale for the long tubes?
It's very hard to understand. Sorry, it's the mask.
But yeah.
So can we ask those questions later? Because there's a question.
Yeah,
from the
because we have a
chat.
question
Oh,
from the
sorry.
chat.
We can, yeah. You're going to send it in after.
Yeah.
Yeah.
Hi, Lívia. So a question from the chat is, for pH-triggered capsules, is carbonation sufficient to decrease the pH of the cracks, especially for some deep cracks?
Who's asking this question?
When, Gianna?
When? Hi, when? That's a very good question. I am going to privately reply you this question because it's part of their homework to think about that as well. And I will leave that for them to think about it when.
Okay. I think that's the end of the talks. Thank you so much.